Namaste. I'm really looking forward to today's deep dive. We're tackling light reflection and refraction, which I know is a cornerstone of Class 10 physics, absolutely critical for the board exams. And, well, it forms a huge part of the foundation for competitive exams like JE and NEET too. I'm hoping we can really unpack it, not just, memorize, but truly understand the core concepts today.
Absolutely welcome. And you've picked a phenomenal topic. Light is fundamental, truly. And mastering reflection and refraction, it really unlocks so much of the physical world around us. From why your spectacles work, to how a camera lens captures an image, or even how those beautiful diamonds get their sparkle. Our mission today is to systematically unravel these concepts, step by step. We want to build that rock-solid foundation for your conceptual clarity and, crucially, for your exam success. We'll go methodically, just like in a dedicated coaching session, ensuring every detail clicks into place. We'll start with the very basics, how we see, the nature of light itself, then we'll plunge into reflection plane mirrors, spherical mirrors. After that, we'll pivot to refraction, exploring how light changes direction, moving through different media and how this applies to spherical lenses. And finally, we'll equip you with the essential formulas, the all-important sign conventions, and concepts like magnification and lens power. These are vital for numerical problems in your exams. So let's kick things off with the absolute simplest question. What actually makes things visible to us? Think about it this way. Imagine walking into a pitch black room. You can't see a thing, right?
Right. Nothing at all.
A flick on the light switch. Suddenly, everything in the room becomes clear. This simple everyday experience tells us something profound. Light is the key ingredient for sight. The fundamental principle is that most objects don't create their own light. Instead, they reflect the light that falls on them. When our eyes receive this reflected light, that's what enables us to perceive those objects. Now, for transparent materials like, say, a clear glass of water, we can see through them because light is transmitted or passes through them. This constant dance between light, objects, and our eyes is the secret behind our ability to see the vibrant world around us. Now, for the phenomena we're focusing on today, reflection and refraction will primarily work with a simplified, yet incredibly powerful model. It's called array optics. This model is built on a very intuitive idea that light travels in straight lines.
Okay, straight lines, that seems straightforward enough.
It does, and we see evidence everywhere. Just hold an opaque object in front of a light source like a torch. What do you see?
A shadow, a sharp one.
Exactly, a sharp, distinct shadow. This crisp shadow is compelling evidence that light, for most everyday scenarios, travels in perfectly straight paths. We represent this straight path as a ray of light, and a collection of these rays forms a beam of light. This straight-line propagation, this ray model, it forms the very backbone for understanding topics like image formation by mirrors and lenses. These are central to your Class 10 syllabus and foundational for JE and NEET. Now, while our focus today relies on this simpler ray model, it's fascinating to know that light holds deeper secrets. It hints at a more complex nature. Just a quick peek into higher physics, something you'll explore in much more detail in Class 11 and 12, especially if you pursue science for JE or NEET. You'll discover phenomena like diffraction of light.
Diffraction, what's that?
Well, it occurs when light encounters an obstacle or an opening that's incredibly tiny, think comparable to light's own wavelength. In such cases, light doesn't just cast a sharp shadow. It surprisingly bends around the edges of the object or through the opening.
It bends around things.
It does, slightly. And this is precisely where our simple ray model, with its strict, straight lines, begins to break down. It can't fully explain diffraction. Historically, scientists were genuinely puzzled by light's true nature. For a long time, there was a big debate. Was it a wave, like ripples in a pond, or was it made of tiny particles, like miniature bullets? The wave theory of light was brilliant. It explained things like diffraction and another phenomenon called interference beautifully. But then, as the 20th century dawned, new experiments, especially those looking at how light interacts with matter, revealed something odd. Light also behaved in some situations like a stream of particles.
So it acts like both a wave and a particle. That seems contradictory.
It certainly seemed that way. It was a major scientific mystery for years. The modern understanding, unified in the quantum theory of light, emerged to reconcile these ideas. In this theory, light isn't exclusively a wave, nor solely a particle. Instead, it exhibits both wave-like and particle-like properties simultaneously. Which property you observe depends on how you measure or interact with it. It's quite a mind-bending concept. However, let's bring it back to our immediate goals, mastering reflection and refraction for your board and competitive exams. For that, sticking to the straight-line propagation model, the ray optics model, is perfectly accurate and sufficient. This foundational understanding will be your key tool for today's deep dive, the exciting world of light's dual nature that awaits you in higher classes.
That's a really interesting glimpse into the more advanced side of physics. So, okay, for our exams now, we're focusing on light as a straight line ray. Got it. That makes sense for building the foundation. What's the very first major phenomenon we're going to unravel then, using this ray model?
Excellent question. The first major phenomenon we'll unpack is reflection of light. In its simplest form, reflection is what happens when light strikes a highly polished surface. Think of a mirror, and bounces back into the same medium it came from. You know, like playing carom, when a striker hits the edge and bounces off.
Yeah, or like a ball hitting a wall.
Exactly.
Yeah.
Light behaves in a remarkably similar way when it hits a smooth, reflective surface. Now, for your exams, understanding the laws of reflection is absolutely crucial. These are the fundamental rules governing how light reflects, no matter the surface shape. The first law is quite straightforward. It states that the angle of incidence is always equal to the angle of reflection. We denote the angle of incidence as A and the angle of reflection as air. So mathematically, it's just air. Now, to really understand these angles, you need to imagine an imaginary line drawn perpendicular to the reflecting surface at the exact point where the light ray hits. We call this line the normal.
The normal, perpendicular to the surface.
Precisely. Think of it as a reference line, pointing straight out from the mirror at that point. The angle of incidence is the angle between the incoming incident ray and this normal. And the angle of reflection is the angle between the outgoing reflected ray and the same normal. This law, error, holds true every single time light reflects. The second law of reflection adds another piece. It states that the incident ray, the normal to the mirror at the point of incidence, and the reflected ray all lie in the same plane.
Same plane. What does that mean exactly?
Imagine a flat sheet of paper representing the plane. If the incident ray comes in along that sheet, and the normal also lies on that sheet, then the reflected ray will also travel out along that same flat sheet of paper. It won't suddenly angle up or down out of the plane. They're all coplanar. And here's a crucial tip, especially for your exams. These two laws are universal. They apply to all types of reflecting surfaces. Doesn't matter if it's a perfectly flat mirror, a shiny spoon, or the curved mirrors we'll discuss soon. These laws always apply. This is a fundamental concept you absolutely must be clear on. Now, you're probably quite familiar with images formed by a plane mirror, right? The kind you use every day.
Yeah, the bathroom mirror. Pretty standard.
Exactly. Let's quickly recap its properties, as these pop up in MCQs or short questions often. When you look at yourself in a plane mirror, you notice a few things. First, the image formed is always virtual and erect.
Virtual meaning, not real. Like you can't project it on a screen.
Precisely. The light rays appear to come from the image location behind the mirror, but they don't actually converge there. And erect simply means it's upright, the same orientation as you are. Second, the size of the image is always equal to the size of the object. No magnification, no shrinking. Third, the image is formed as far behind the mirror as the object is in front of it. Distance is conserved, in a sense.
Okay, so same distance, same size.
Right, and finally, the image is laterally inverted.
Ah, the left-right swap.
Exactly. Your right hand appears as the left hand in the image. That's lateral inversion. It's why ambulance is written backwards on the front of emergency vehicles.
Oh, so drivers see it correctly in their rearview mirrors. Clever.
Precisely. It's a direct application of lateral inversion. So those are the key features. Virtual, erect, same size, same distance behind, and laterally inverted.
Understood. That makes perfect sense. Plane mirrors are pretty straightforward, and that ambulance example really clicks. But what happens when the reflecting surfaces aren't flat? Like you mentioned spoons or those funny mirrors at fairs. The curved ones, how do they work?
That's the perfect transition. Curved surfaces are where optics gets really interesting and opens up a whole new range of possibilities for image formation. Let's use that spoon example again, like in Activity 9.1. If you look at your face in the inner curved inward surface,
The side you eat with.
yes, that side, you'll notice your image might look upside down, maybe bigger or smaller, depending on how close you hold it. Now, flip the spoon over and look at the outer bulging outward surface.
Okay.
What do you see now? Probably an upright image, right? And likely smaller. And you can probably see more of the room behind you reflected.
Yeah, definitely upright and smaller. And I can see more around me.
See, this simple experiment shows that the image characteristics, size, orientation, real virtual change dramatically based on the curvature and the object's distance. This leads us directly to spherical mirrors. Spherical mirrors, as the name suggests, are mirrors whose reflecting surfaces are part of a larger sphere. Imagine cutting a piece out of a hollow mirrored ball. There are two main types. First, the concave mirror, Its reflecting surface curves inwards, like the inside of that spoon or a cave entrance. It faces towards the center of the sphere it came from. In diagrams, we usually shade the outer non-reflecting side.
Okay, concave curves inwards.
Second, the convex mirror. Its reflecting surface curves outwards, like the back of the spoon. It bulges towards you. Here, the inner non-reflecting side is shaded in diagrams.
Got it. Convex bulges outwards.
These two types behave very differently due to their shapes, leading to very different images. Before we see how they form images, we need to define some absolutely key terms. These are fundamental building blocks and often appear as definition questions in exams, so let's be precise. First, the pole, P. This is simply the geometric center of the mirror's reflecting surface. It lies right on the mirror. Think of it as the mirror's central point, our main reference. Next, the center of curvature, C. Remember the imaginary sphere the mirror was cut from? The center of that sphere is the center of curvature, C. Now here's a crucial point. C is not on the mirror's surface itself. It's out in space. For a concave mirror, curving inwards, C is in front of the mirror. For a convex mirror, bulging outwards, C is behind the mirror.
Okay, so C depends on the type of mirror.
It does. Then there's the radius of curvature, R.
Yeah.
This is just the radius of that original imaginary sphere. It's the distance from the pole, P, to the center of curvature, C. So R is 6 in PC. The principal axis is a very important imaginary line. It's the straight line that passes right through the pole, P in the center of curvature. So think of it as the main axis of symmetry for the mirror. Now, a really important one, the principal focus, F. You can understand this best through an activity like Activity 9.2. Imagine taking a concave mirror and pointing it towards the sun. The sun's rays are coming from very far away, essentially parallel to each other. The concave mirror will gather all these parallel rays and converge them, focus them, onto a single tiny bright spot on its principal axis. This spot can get hot enough to burn paper.
Ah, like using a magnifying glass, but with a mirror?
Similar concentrating effect, yes. That point where the parallel rays converge is the principal focus, F, of the concave mirror. For a concave mirror, F is a real point in front of the mirror. Now, for a convex mirror, it behaves differently. It diverges parallel rays. When parallel rays hit a convex mirror, they bounce off and spread out. But if you trace these reflected rays backwards, they appear to be coming from a single point behind the mirror on a principal axis. That point is the principal focus F of the convex mirror. Since the rays only appear to come from there, it's a virtual focus.
So concave has a real focus in front, convex has a virtual focus behind.
Exactly. And the distance from the pole, P, to this principal focus F is called the focal length F. It's a measure of how strongly the mirror converges or diverges light. Lastly, the aperture is just the effective diameter of the mirror's reflecting surface. We usually deal with mirrors of small aperture, meaning the diameter is much smaller than the radius of curvature. This simplifies things. Now here's a super important relationship connecting two of these terms, the radius of curvature, R, and the focal length, F. For spherical mirrors with small apertures, it's experimentally found and can be geometrically shown that the radius of curvature is exactly twice the focal length. This gives us the vital formula. R equals 2F.
R equals 2, so the radius is double the focal length.
Precisely. Or, put another way, the focal length is half the radius of curvature. F equals R2. What does this mean physically? It means the principal focus, F, lies exactly midway between the pole P and the center of curvature, C.
Yep.
It's perfectly positioned halfway. This is a very frequently used relationship in problems.
Okay, so P, C, F, and the principal axis are like our map coordinates for mirrors. And R equals 2F is a key connection, putting F right in the middle between P and C. I'm starting to get a picture. Now, the big question, how do these mirrors actually form images? You mentioned drawing rays. I know those ray diagrams are super important for exams. How do we do that?
Fantastic question. And yes, mastering ray diagrams is absolutely central. Understanding image formation relies heavily on them. The key idea is that the image's nature, real, virtual, inverted, direct, its position, and its size, all depend on where you place the object relative to P, F, and C. To find the image, we use ray diagrams. An object emits countless rays, but thankfully, we only need to trace the paths of two specific, easy-to-predict rays after reflection. Where these two reflected rays intersect, or appear to intersect if we trace them backward, is where the image of that point on the object is formed. Let's break down the 4 standard rays used. Mastering these is non-negotiable for boards and competitive exams. Here are the 4 key rays, step by step. Rule number 1. A ray traveling parallel to the principal axis. After reflection from a concave mirror, this ray passes directly through the principal focus, F. After reflection from a convex mirror, this ray appears to diverge from the principal focus, F, located behind the mirror. Trace the reflected ray back and it'll point to F.
Okay, parallel ray goes through F concave, or appears to come from F convex.
Rule number 2. This is basically the reverse of Rule 1. A ray passing through the principal focus F of a concave mirror, or a ray directed towards the principal focus F of the convex mirror. After reflection, this ray emerges parallel to the principal axis.
So ray through F becomes parallel. Makes sense, it's reversible.
Rule number 3. A ray passing through the center of curvature, C, of a concave mirror, or directed towards the center of curvature, C, of a convex mirror. After reflection, this ray reflects straight back along the same path. It retraces its steps.
Back along the same path. Why?
Good question. Because any line passing through C strikes the spherical mirror surface perpendicularly along the normal. And a ray hitting along the normal angle of incidence equals 0 reflects back along the normal angle of reflection. Your error. And rule number 4. A ray incident obliquely at an angle towards the pole, P. This ray reflects obliquely following the basic law of reflection. The principal axis itself acts as the normal at the pole. So the angle the incident ray makes with the principal axis equals the angle the reflected ray makes with it.
Okay, basically bounces off the pole symmetrically respecting the axis.
Exactly. And remember, you only need to accurately draw any two of these 4 rays from a point on the object. Where the reflected rays intersect, or appear to intersect, pinpoints the image location for that point. Practice drawing these. Clear, accurate diagrams are crucial for exams. Let's now apply these rules to image formation by a concave mirror. This is where we see a variety of image types, depending on the object's position. Think back to activity 9.3, maybe with a candle. We'll go through the cases systematically, like in table 9.1 in your textbook. Object at infinity, like the sun. Parallel rays come in. Where do they converge?
At the focus.
F, correct. Image at F, it's highly diminished, point-sized, real, and inverted. Think solar cookers. Object beyond C. Image formed between F and C. It's smaller, diminished, and still real and inverted. Object exactly at C. Where's the image?
If R2F, maybe it's C2.
Precisely. Image formed exactly at C. It's the same size as the object and still real and inverted. This is a key symmetrical point. Object between C and F. The image now forms beyond C. It becomes enlarged and remains real and inverted. Object exactly at F. What happens to rays starting from F?
Rule 2 says they become parallel after reflection.
Right. The reflected rays are parallel. They never meet or meet at infinity. So image is formed at infinity, highly enlarged, real, and inverted. This is the principle behind searchlight's bulb at F gives a parallel beam, and the special case. Object between P and F. This is the only case where a concave mirror gives a virtual and erect image. The reflected rays diverge, but appear to come from a point behind the mirror. The image is enlarged.
That's the shaving mirror or dentist's mirror case. Magnified and upright.
Exactly. That's the one. See the pattern. As the object moves from infinity towards the pole, the image moves from F through C out towards infinity, and then flips behind the mirror for the last case. Its size also changes systematically. Understanding this pattern is key, and the uses directly follow from these properties we mentioned. Torches, searchlights, vehicle headlights, bulb at F to get a parallel beam, shaving mirrors, dentist mirrors, object between P and F for a magnified, erect, virtual image, solar furnaces, large concave mirrors concentrating sunlight at F to produce heat.
That's really clear how the object position dictates the image and the use. Concave mirrors are quite versatile. What about convex mirrors? Are they simpler? Do they have this many possibilities?
Good question. Convex mirrors are indeed much simpler in terms of image formation. Remember activity 9.5, looking at a pencil?
Yeah, I think it was always upright and smaller, right?
Exactly. That's the key takeaway. Convex mirrors behave very consistently. Let's look at the 2 main cases for a convex mirror. Table 9.2. Object at infinity. Parallel rays come in. Where they appear to diverge from after reflection.
From the focus, F, behind the mirror.
Correct. Image formed at F, behind the mirror. It's highly diminished, point-sized, virtual, and erect. Object anywhere between infinity and the pole. P. This covers every other possible position. The image is always formed between P and F, behind the mirror. It is always diminished and always virtual and erect. So the crucial difference. A convex mirror always forms a virtual, erect, and diminished image, regardless of the object's position. Always, always, always.
Wow, okay. That is much simpler. Always virtual, always erect, always smaller.
This predictable behavior, combined with another property, makes them perfect for a very specific common use. Think about activity 9.6, trying to see a large building in a small convex mirror.
You can see the whole thing, even if it's huge.
Right. Convex mirrors provide a wider field of view than plane or concave mirrors of the same size. Because they curve it outwards, they gather light from a larger area. And this leads directly to their main application, a very frequent exam question. Rear viewing mirrors in vehicles. Why convex? 2 reasons. First, they always give an erect image. Essential for driving safely, you don't want inverted cars behind you.
Definitely not.
Second, they offer that wider field of view, allowing the driver to see much more of the road and traffic behind them, reducing blind spots.
Right. Safety again.
Yeah.
Wider view, upright image. Makes perfect sense. I should remember those 2 points.
Excellent. So we've covered image formation qualitatively. Now we need the tools for quantitative analysis, the calculations. Before we jump into formulas, we absolutely need a consistent system for measuring distances and heights. This is the new Cartesian sign convention. Getting this right is non-negotiable for solving numerical problems correctly. One sign error can completely derail your answer. Let's break down the rules. Imagine a standard XY coordinate plane with the mirror's pole at the origin. 1. Origin is the pole. P. All distances are measured from the pole of the mirror. P is our 0, 0. 2. Principal axis is the x-axis. Simple enough. 3. Object is to the left. By convention, the object is always placed to the left of the mirror. So light travels from left to right towards the mirror.
Okay, object always on the left side.
4. Distances along the x-axis. Distances measured to the right of P, positive x direction, are positive. Plus, distances measured to the left of P, negative x direction, are negative. 5. Heights, perpendicular to the principal axis. Heights measured upwards from the principal axis, positive y direction, are positive plus. Objects are usually placed upright, so object height h is usually positive. Heights measured downwards from the principal axis, negative y direction, are negative. Inverted images have negative height h. Now, applying this specifically to focal length, for a concave mirror, f is in front, left of P, so its focal length f is negative. For a convex mirror, f is behind, right of P, so its focal length f is positive. Got it. Concave f negative, convex f positive. That's a key sign rule. So the origin is always at the pole, and we follow a standard sign system like in math class. This makes sense for consistency. Are there specific formulas that use these conventions then? Yes, absolutely. These conventions are the language we use to speak to the formulas correctly. Let's define the variables again, keeping signs in mind. Object distance, u. Distance from P to the object. Since the object is always left, u is almost always negative. Image distance, v. Distance from P to the image, its sign tells us the location. Negative v means real image in front for mirrors. Positive v means virtual image behind for mirrors. Focal length f, distance from P to f, negative for concave, positive for convex. Now the big one, the mirror formula. This beautiful equation connects these 3 quantities, 1v plus 1u equals 1 over f. Okay, that's the one, equation 9.1. It works for all spherical mirrors, concave or convex, for any object position. The absolute key, I repeat, is to substitute the values of u, v, f, and r, since f or r, with their correct signs according to the new Cartesian sign convention. Every single time. No exceptions. Now, besides where the image is, we often need to know how big it is compared to the object. That's magnification, m. Magnification tells us the relative size and orientation. 2 ways to calculate it. First, using heights, MP equals OH, equation 9.2. That's image height divided by object height. Second, using distances, M ample of U, equation 9.3. Note the minus sign here. Magnification is the negative ratio of image distance to object distance for me.
Okay, M equals HH or M equals minus view. Got it.
Yeah. The sign of M tells you about the image orientation instantly. If M is negative, the image is real and inverted, because H would be negative. If M is positive, the image is virtual and erect, because H would be positive. And remember, object height H is usually positive, upright object. Ready to try applying these with some actual numbers? Let's walk through the examples carefully. Example 9.1. A convex rear view mirror has R plus 3.00 meters. A bus is at U equals 5.00 meter. Find V and the nature size.
Okay, convex mirror, so R is positive, object distance U is always negative. Got it.
Step 1. Find focal length, F. We know R, it's 2, F, so F is R2, F plus 3.0 meter. 2 equals plus 1.50 meter. Causative F checks out for convex.
Okay, S is plus 1.5 on here.
Step 3. Substitute values with signs. 1V equals 1 plus 1.50, 1 to 500, 1V, 1 PLE 11.5 plus 15.0.
Minus minus becomes plus. Okay.
Step 4. Solve for a V. Find a common denominator, maybe 7.50. 1V equals 5.00, 7.50 plus 1.50, 7.50, 6.50. So 7.50, 7.50. So V equals 1.50, 6.50 plus 1.150.
Positive V means the image is behind the mirror and virtual.
Exactly. Image is 1.15 meters behind the mirror. Positive V confirms it's virtual for a mirror. Step 5, calculate magnification. M equals leads your field. M equals 0 Lear plus 1.151000 equals plus 0.23.
Positive M, so virtual and erect. And 0.23 is less than 1, so it's smaller, diminished.
Perfect interpretation. Step 6, State the result clearly. The image is virtual, erect, diminished, size is 0.23 times the object, located 1.15 meters behind the mirror. That matches what we expect for a convex rearview mirror. Let's do example 9.2. Concave mirror. Object height h equals plus 4.0 centimeters. Object distance u equals 25.0 centimeters. Focal length f equals 15.0 centimeters. Concave, so negative f. Find v and h.
Okay, concave mirror, u is negative, f is negative, h is positive, need v and h.
Step 1, mirror formula. 1v plus 1u equals 1f. Rearrange 1v equals 1f, 1u. Step 2, substitute with signs. 1v omega over 15.0, 125.0. 1v equals 1 negative 75.0 plus 315, 50, 75, 1 Step 3, solve for vv. We're going to see 37.5 centimeters.
Negative v this time. So image is in front of the mirror, and it should be real.
Precisely. A screen should be placed 37.5 centimeters in front of the mirror to get a sharp image. It's real. Step 4, calculate magnification. Have m and at 37.5 centimeters, and it was 25.0 centimeters. M at plus 37.5, 25.0 equals 1.5.
Negative m confirms real and inverted, and magnitude 1.5 is greater than 1, so it's enlarged.
Excellent. Step 5, calculate image size h. Using m and h, so h image, and he is 1.5 plus 4.0 centimeters, confirms inverted. Size is 6.0 centimeters, which is larger than the 4.0 centimeter object. Enlarged. Checks out.
Perfect. Step 6, state clearly. Screen at 37.5 centimeters in front. Image is real, inverted, enlarged, 6.0 centimeters tall.
Wow, okay. Applying the sign convention properly is absolutely critical. I can see how just one slip up with a plus or minus sign could completely mess up the whole problem and the interpretation. These examples really help to break it down, so that seems to cover reflection pretty well. What's next on our agenda? What happens when light goes through things instead of bouncing off? That's the perfect transition, leading us to the second major phenomenon, refraction of light. This is just as important as reflection for your exams and for understanding everyday optical effects. Before the formal definition, think about some things you've likely observed. Ever looked into a swimming pool and felt the bottom look shallower than it really is?
Yeah, definitely. It looks raised up.
Or put a pencil in a glass of water? It looks bent or broken at the surface, right?
Uh-huh. Always looks weird.
Or maybe seen letters under a thick glass paperweight appear raised. Or a lemon in water looking bigger.
Yeah, I think I've seen those effects.
Exactly. All these observations, including textbook activities like trying to grab a coin in a bucket, activity 9.7, or making a coin disappear, activity 9.8, point to the same thing. Light changes its direction when it travels obliquely, meaning at an angle, from one transparent material into another.
So it bends when it crosses from, say, air to water.
Precisely. That bending is refraction. Formally, refraction is the phenomenon of the change in the direction of propagation of light when it travels obliquely from one transparent medium to another. Let's visualize this with the classic experiment. Refraction through a rectangular glass slab. Activity 9.0, figure 9.1L. Imagine a ray of light going from air into the glass slab and then back out into the air. We observe two key bends. First, as light enters the glass, denser medium, from air, rarer medium, it bends towards the normal. Remember the normal line perpendicular to the surface. The light ray bends closer to it.
Okay, rarer to denser bends towards normal.
Second, as light exits the glass, denser back into the air, rarer, it bends away from the normal. It bends further away from that perpendicular line.
Denser to rarer bends away from normal.
Correct. And an interesting result for a rectangular slab is that the emergent ray coming out is parallel to the incident ray going in, but it's shifted sideways. This is called lateral displacement. Now, why does this bending happen? What's the underlying cause? Refraction occurs because the speed of light changes as it enters a different transparent medium. Light travels at different speeds in different materials. This change in speed forces the change in direction unless it enters exactly along the normal perpendicularly.
Ah, so the speed change is the key reason for the bending.
Just like reflection, refraction also follows specific laws, the laws of refraction. Law 1. The incident ray, the refracted ray, and the normal to the interface at the point of incidence all lie in the same plane. Just like reflection's second law, it ensures everything stays in 2D for that interaction.
Okay, same plane again.
2. Law 2. Snell's law of refraction. This one is extremely important. A cornerstone of optics. It states, for a given pair of media and for light of a given color, the ratio of the sign at the angle of incidence, sin I, to the sign of the angle of refraction, sin R, is a constant. Mathematically, sin I, sin R equals constant, equation 9.4. This constant value is characteristic of the two media involved and is called the refractive index.
Sin R equals constant, Snell's law, and that constant is the refractive index. Got it. That sounds really important for calculations. Okay, so light changes speed and direction when it moves between different materials, causing the bending. And Snell's law, sin I over sin r, gives us a constant value for that change. What exactly is this refractive index then? How does it quantify the bending, and what does it tell us about the material itself?
Precisely the right question. The refractive index n is that constant from Snell's law. Think of it as a number that tells you how much a particular transparent medium bends light. It's a fundamental property of the material itself, and it's directly linked to the speed of light. As we said, light travels fastest in a vacuum. We call this speed c, about 3 by 108 meters. In air, it's almost as fast, but in denser materials like water or glass, it slows down considerably. This change in speed is what the refractive index quantifies. We define refractive index in two main ways. First, relative refractive index. If light goes from medium 1, speed v1, to medium 2, speed v2, the refractive index of medium 2 with respect to medium 1, written as n21, is n21, speed of medium 2, v2, equation 9.5. It compares the speeds in the two media. Second, and more common, is the absolute refractive index, nm. This compares the speed of light in a medium v to the speed of light in vacuum c. For practical purposes, we often use the speed in air instead of vacuum, as they're very close. So the absolute refractive index n of a medium is n equals speed of light in air, c, speed of light in the medium, equation 9.7. So when you see refractive index of water is 1.33, table 9.3, it means light travels 1.33 times slower in water than in air or vacuum.
So a higher refractive index means light travels slower in that medium.
Exactly, like diamond with 2 and 2.42. Light slows down a lot in diamond, which is why it bends so much and gives that characteristic sparkle through phenomena like total internal reflection. You don't need to memorize all the values in table 9.3, but understand what they mean. Higher, Samad-Matin, means slower speed and more bending potential. Now let's clarify optical density versus mass density. This often trips students up. When we say denser medium in optics, we mean optically denser, not necessarily heavier or having more mass per volume. Optical density refers to the ability of a medium to refract light. A medium with a higher refractive index is optically denser. It's crucial to know they aren't the same. For example, kerosene has a lower mass density than water. It floats on water, but it has a higher refractive index, around 1.44 versus 1.33 for water. So kerosene is optically denser than water, even though it's lighter.
Okay, that's a really important distinction. Optical density relates to refractive index, not mass density.
And this connects back to the bending rule. Light going from rarer to denser, lower N to higher N, slows down, bends towards the normal. Light going from denser to rarer, higher N to lower N, speeds up, bends, away from the normal. Think of the traffic analogy again. Highway, rarer, to city street, denser, you slow down and steer inwards towards normal. City street, denser to highway, rarer, you speed up and steer outwards, away from normal.
So refractive index quantifies the bending, linked to speed change. And optical density is about this refractive property, not just weight. That traffic analogy really helps visualize the towards-way bending. Okay, so that's refraction with flat surfaces like slabs. What about curved transparent surfaces like spectacle lenses or magnifying glasses? How do they use refraction?
Exactly. Curved transparent surfaces are the basis for lenses, which are incredibly important optical devices. Think watchmakers' loops, spectacles, cameras, microscopes, telescopes, all rely on lenses. What is a lens? It's a piece of transparent material, like glass or plastic, bounded by two surfaces, where at least one surface is spherical, curved. It could be two curved surfaces, or one curved and one flat. Just like mirrors, there were two main types of spherical lenses. First, the convex lens. It's thicker in the middle and thinner at the edges. Usually both surfaces bulge outwards. Its key action is to converge parallel light rays, bring them together at a point. That's why it's also called a converging lens.
Convex converges light, like a magnifying glass focusing sunlight.
Second, the concave lens. It's thinner in the middle and thicker at the edges. Usually both surfaces curve inwards. Its key action is to diverge parallel light rays, spread them out. So it's also called a diverging lens.
Concave diverges light, spreads it out.
Now, the key terms for lenses. Similar to mirrors, but with some key differences because lenses have two surfaces and work by refraction. Since a lens has two spherical surfaces, it has two centers of curvature, C1 and C2, one for each surface's sphere. The principal axis is the imaginary line passing through both C1 and C2. The optical center O is the very central point of the lens. It has a crucial property. A ray of light passing exactly through O goes straight through without any deviation or bending. This is super useful for ray diagrams.
The optical center is like a free pass through the lens, no bending there.
Exactly. The aperture is the effective diameter of the lens. We mostly consider thin lenses with small apertures. Now, principal focus. Lenses have two principal foci, f1 and f2, one on each side, usually equidistant from O for thin lenses. Think activity 9.11, using a convex lens to focus sunlight. The point where parallel rays converge after passing through the lens is the principal focus, usually called f2. Since rays actually meet there, it's a real focus. For a concave lens, parallel rays diverge after passing through. If you trace these diverging rays backward, they appear to come from a point on the principal axis on the same side as the incoming light. This point is a principal focus, usually f1. Since rays only appear to come from here, it's a virtual focus.
So convex lens has a real focus where light converges, concave has a virtual focus where light appears to diverge from, and two foci for each lens?
Correct. And the distance from the optical center O to where the principal focus f1 or f2 is the focal length f.
Okay, so lenses work by refraction, have two C's and two F's, and that optical center O where light goes straight. How do we draw ray diagrams for them, and what kinds of images do they form? It feels similar to mirrors, but I bet the rules for rays are different because it's refraction now, not reflection.
You're absolutely right. The rules are adapted for refraction. Ray diagrams for lenses are just as crucial as for mirrors. We again use specific rays, but now we trace them through the lens. We generally use 3 key rays for lenses, and you only need 2 to find the image. Let's break down the 3 standard rays for lenses. Rule number 1, a ray parallel to the principal axis. After refraction through a convex lens, this ray passes through the principal focus f2 on the other side of the lens, converging action. After refraction through a concave lens, this ray appears to diverge from the principal focus f1 on the same side as the incident ray, diverging action.
Okay, parallel ray goes to F2, or seems to come from F1 concave.
Rule number 2, a ray passing through the focus. For a convex lens, a ray passing through the first principal focus f1 emerges parallel to the principal axis after refraction. For a concave lens, a ray directed toward the second principal focus f2 emerges parallel to the principal axis after refraction.
So ray through F1 convex or towards F2 concave becomes parallel. Again, reversible.
Rule number 3, the easiest one, a ray passing through the optical center O. This ray emerges from the lens without any deviation, goes straight through.
Undeviated through O. That one seems the most straightforward to draw.
It usually is. So pick any 2 of these 3 rays from a point on the object. Where the refracted rays, or their backward extensions, intersect is where the image of that point is formed. Now let's look at image formation by a convex lens. You'll notice strong parallels to the concave mirror cases. Object at infinity. Image at f2. Highly diminished, real, and inverted. Object beyond 2f1. 2f1 is like the C point for lenses. Image between f2 and 2f2. Diminished, real, and inverted. Object exactly at 2s1. Image exactly at 2f2. Same size, real, and inverted. The symmetrical point again.
Object at 2f1, image at 2f2, same size. Like object at C, image at C for concave mirrors.
Exactly the same pattern. Object between f1 and 2f1. Image beyond 2f2. Enlarged, real, and inverted. Object exactly at f1. Refracted rays become parallel. Image at infinity. Highly enlarged, real, and inverted. The special case. Object between O and f1. This is the only case for a convex lens giving a virtual and direct image. It's formed on the same side as the object, and it's enlarged. This is the magnifying glass case.
Right. Object close up, you get a big upright virtual image.
See the pattern. Very similar progression to the concave mirror as the object moves closer. Understanding these parallels can really help with recall.
That pattern matching is definitely useful. So convex lens acts much like a concave mirror in terms of image types. What about the concave lens then? Is it like the convex mirror, simple and predictable?
You've got it. The concave lens behaves very consistently, just like the convex mirror did. Think activity 9.13, looking through 1. There were essentially only 2 cases for a concave lens, table 9.5. Object at infinity. Image formed at f1 on the same side as the object. Highly diminished, virtual, and erect. Object anywhere between infinity and O. The image is always formed between f1 and O, on the same side as the object. It is always diminished and always virtual and erect. So the key takeaway, a concave lens always forms a virtual, erect, and diminished image, regardless of the object's position. Simple and predictable.
Okay, concave lens, always virtual, always erect, always diminished. That's a helpful pairing to remember.
Excellent. Now, before we tackle numericals for lenses, we need the sign convention for spherical lenses. It's very similar to mirrors, but centered on O, and with a key difference for F. The rules. 1. Measurements in the optical center, O. O is the origin. 2. Principal axis is the x-axis. 3. Object to the left, light comes from the left, so U is usually negative. 4. Distances right of O are positive, plus. 5. Distances left of O are negative. 6. Heights upwards from axis are positive, plus. Object height h usually plus. 7. Heights downwards from axis are negative. Inverted image height h is blank. Now, the crucial part for lens focal length. Convex lens converges light to a real focus f2 on the right. Its focal length f is positive. Concave lens diverges light from a virtual focus f1 on the left. Its focal length f is negative.
Okay, that's opposite to mirrors for focal length signs relative to type. Convex lens f positive, concave lens f negative. Got it.
With those signs clear, let's introduce the lens formula and magnification for lenses. Again, pay close attention to the differences for mirrors. The lens formula relates u, v, and f for lenses. 1v, 1u equates 1f, equation 9.8.
Whoa, hold on. That's a minus sign between 1v and 1u. Mirrors had a plus.
Exactly. That's the key difference you must remember. Lens formula. 1v, 1u equals 1f. Mirror formula. 1v plus 1u equals 1f. Mix these up, and the answer will be wrong. Again, apply sign convention strictly when using this formula. Now, magnification m for lenses. Definition is the same. Ratio of image height to object height. M forge, equation 9.9. But the distance formula is different for mirrors too. For lenses, m equals vu, equation 9.0.
So it's vu, no minus sign like mirror.
Correct. Lens magnification m equal vu, mirror magnification m equal vu are another critical difference to burn into memory. The interpretation of the sign of m remains the same though. Negative m, real and inverted image. Positive m, virtual and erect image. And magnitude tells you about size, m1 enlarged, m1 diminished, m1 same size. Let's try applying these lens formulas. Example 9.3, concave lens, f equals negative 15 centimeter, negative for concave, forms an image at v equals negative 10 centimeters. Concave lens always forms virtual image on same side, so v is negative. Find object distance u and magnification m.
Okay, f is a minus 15, v is minus 10. Need u and m. Use the lens formula with the minus sign.
Step 1, lens formula. 1v, 1u equals 1f. Rearrange for 1u. 1u was 1v, 1f. Step 2, substitute with signs. 1u equals 110, 115. 1u equals 1a is 110 plus 115.
Common denominator 30. 1u equals mate equals 3d 30 plus 230 equals ln of 130.
Perfect. Step 3, solve for u equals 30 centimeter. Negative u makes sense. Object is always on the left, so 30 centimeters in front.
Step 4, calculate magnification. M of v, the lens version, m n of is 10 centimeters and n is 30 centimeters plus 13 plus 0.33.
Positive m means virtual and erect. Magnitude 0.33 is less than 1, so diminished. Checks out for a concave lens.
Excellent. Now, example 9.4, convex lens. Object height h is plus f is plus 10 centimeters, positive for convex. Object distance u is 15 centimeters. Find vh and m.
Okay, convex lens h is plus f is plus n is might need vhm.
Step 1, lens formula. 1v, 1u equals 1f. Rearrange for 1v. 1v is 1f plus 1u. Step 2, substitute with signs. 1v is 1 plus 10 plus 115.
Yes, step 3, solve for vv plus 30 centimeters.
Positive v for a lens. This means image is on the other side and should be real.
Exactly. Image formed 30 centimeters on the opposite side of the lens. It's real. Step 4, calculate magnification. M equals m equals plus 30 centimeters, negative 15 centimeters, negative 2.
Negative m, real and inverted. Magnitude 2 means enlarged.
Step 5, calculate image size, h, using MHAH, so h(2) plus 2.0 centimeters, negative h confirms inverted. Size 4.0 centimeters, twice the object's 2.0 centimeters, enlarged. Everything matches.
Close analysis.
The lens formula and magnification calculations, especially remembering the sign differences from mirrors, are definitely tricky. But breaking it down step by step like that makes it much clearer how to avoid mistakes. That's been super helpful for lenses. What's the final concept for lenses we need to cover? Something about spectacles, maybe? Yes, exactly. The final key concept, directly related to applications like spectacles, is the power of a lens. We've seen that lenses bend light, converging or diverging it. How strongly they bend light depends on their focal length. A lens with a short focal length that bends light sharply has a strong effect. A lens with a long focal length bends light more gently. This bending ability, or the degree of convergence or divergence, is quantified by the power of the lens. Power P is defined very simply as the reciprocal of the focal length, F. P equal 1F, equation 9.1. The SI unit of power is the dioptry D. You've probably heard this unit from optician prescriptions. 1 dioptry is the power of a lens with a focal length of 1 meter, so 1D equals 1 ni. Crucially, to calculate power in dioptries, the focal length must be in meters. If you're given F in centimeters, convert it to meters first, divide by 100 before calculating P equals 1F.
Okay, P equals 1F, unit is dioptry D, and F must be in meters for dioptries.
Got it. The sign of the power immediately tells you the lens type. Convex lens, F is positive, P is positive, plus V power, converging lens. Concave lens, F is negative, UB is negative. Negative V power, converging lens.
So the sign of the power prescription plus 2.0D or negative 2.5D directly tells the optician if it's convex or concave.
Precisely. That's its practical use. Plus 2.0D means convex. S of S plus 0.5 meters plus 50 centimeters plus 50 centimeters plus 50 centimeters means concave. F1 negative 2.5 negative 0.4 meters and negative 40 centimeters. Very convenient. Another important thing, especially for complex systems and competitive exams, combination of lenses. If you place several thin lenses in close contact, the total power B of the combination is simply the algebraic sum of their individual powers, P1, P2, P3. Just add them up, respecting the signs. P1 plus P2 plus P3 plus F.
Wow, just simple addition. That's handy.
Extremely handy. It's used by opticians when testing eyes by combining trial lenses and by engineers designing complex optical instruments like cameras or telescopes to control the overall focusing and minimize defects.
So power is 1 over F in meters, measured in dioptries, positive for convex, negative for concave. And powers just add up when lenses are combined. That's quite neat and explains a lot about spectacles. It's amazing how these principles explain everything from a mirage to how my camera works.
It truly is. Light governs so much of how we perceive and interact with the world. And that brings us to the end of our deep dive into light reflection and refraction. So let's quickly recap the key takeaways. We started with the basics, how light makes things visible, and the ray optics model. Then we master the laws of reflection, image formation by plane and spherical mirrors, concave and convex, understanding their properties and uses. We nail down the crucial terms like P, C, F, and the RU to F relation. Then we shifted to refraction, understanding why light bends, a speed change, quantified by refractive index and Snell's law, sin, I sin, Ariel's constant. We applied this to spherical lenses, convex and converging, concave, diverging, learning their terms, O, C1, C2, F1, F2, and image formation patterns. Crucially, we covered the new Cartesian sign convention and applied it meticulously to the mirror formula 1V plus 1U equals 1F and the lens formula 1U equals 1F, noting the key sign differences. We also covered magnification for both, amplitude for mirrors and U for lenses. Finally, we wrapped up with the power of a lens, P1F, in dioptries and how powers combine. This chapter, as you know, is packed with concepts and numericals. It's absolutely fundamental for Class 10 and beyond, especially for JNE and NEET. My advice for your exams: revise these concepts thoroughly. Practice drawing those ray diagrams until they are perfect. They often carry significant marks. Solve numerous numerical problems, focusing intensely on applying the sign conventions correctly. Consistency in practice is truly the key here. Understand the why behind the formulas. Don't just memorize. Here's a thought to leave you with. Look around your home, your school, your city. How many devices or phenomena can you spot that clearly demonstrate reflection or refraction? Your glasses, a camera phone lens, the way light shimmers on water, a simple spoon, the rear view mirror in a car. Try to identify the type of mirror or lens involved and why it's used there based on the principles we discussed today. It makes the physics come alive. And of course, if any doubts remain or you want to tackle more complex problems, always feel free to ask. Keep learning, keep questioning, and keep exploring the fascinating world of light.
Thank you so much. That was an incredibly clear, thorough, and really helpful deep dive. I feel much more confident about tackling light, reflection, and refraction now, especially with the patterns and those crucial sign conventions nailed down. I'll definitely be practicing the diagrams and numericals, and I'm already starting to look at things differently, spotting the optics. Looking forward to our next session.